We define the convolution as this strange integral of a product of two functions, one of which is shifted. Now, of course, you can write this product inside the integral in any form you'd like. Now, the real utility of this convolution is that it allows us to evaluate the inverse of a product. Now, why does that serve us well? When we solve initial value problems. So if I were to take this expression, apply the Laplace transform, I'd get s squared capital Y of s minus sy of 0 minus y prime of 0, subtract y of s is going to be some capital F of s. Each of these initial conditions is 0 in this particular problem. We'll have s squared minus 1 capital Y of s is capital F of s. And what we'll find is that the Laplace transform of our solution is given by this expression, 1 over s squared minus 1 times f of s. Now, as we've discussed, this is the transfer function for our particular differential equation. It somehow encodes information about the left-hand side, and the denominator of this thing, when it's 0, its poles give us useful information about the solution. The solution, in fact, is found by taking the inverse of that solution, the y of s, and this is where the convolution kicks in. We've got the inverse transform of this product, and this is where the convolution theorem kicks in, and it says you can write the solution here as an integral from 0 to t, and it will be related to these two things. Now, even before I go on, I should say a little bit more clearly, a better way to write this would be to say it would be the inverse Laplace transform of that expression convolved with this thing here. And that would lead us to an integral 0 to t. We would have this expression. This is a sinh function, but it would be shifted t minus tau according to the convolution theorem, and we would have f of tau d tau. And that is our solution. Now, if you wanted to, you could write this in terms of its definition. It would be 1/2 e to the t minus tau subtract e to the negative t minus tau. And then we'd have our f of t d tau. Now remember, you can swap out that right-hand side anytime you want. We want to compare this with our Green's function expressions that we've always been using. If we were to go ahead and solve this problem using the quote-unquote old way of doing things, we would end up with a particular solution that looked just like this. Now remember, we aren't going to use the letter s here for our dummy variable. What we are going to use is a tau. And when you compare this, you can see that what's happening is that this thing right here turns out to be the Green's function. Now, if we trace this back, in this particular example, where did the Green's function relate to? From this example, we can see that the Green's function turned out to be 1/2, actually all that exponential business, right? We could write it out. T minus tau subtract negative t minus tau. But what's most important is that we make this connection. It turned out to be the inverse Laplace transform of this thing, which was the inverse Laplace transform of the system transfer function. And this turns out to be a general situation. In general, we have a new way to find the Green's function. And I think this is a really good thing. That's a smiley face. We've got a new way to find the Green's function. The Green's function is going to be the inverse Laplace transform of the system transfer function. And then all we do is we shift the answer to t minus tau. That's it. So much easier. So much easier than what we were doing before, where you would take this thing, where we used an s, but we would use a tau now, and we would have to go y1 of tau, y1 of t, y2 of tau, y2 of t, over the Wronskian in tau. That's a lot of work. This thing, much, much, much easier. It's much easier to find this thing by simply using the inverse of the system transfer function. Now, a while ago in the course, I also said something about Green's functions. Green's functions will always be shifted. They will always be this particular combination of t and tau. You will always be able to write a Green's function in terms of this shift. And that's very, very handy. So the convolution is not only a way to undo a Laplace transform of a product, but it's a way for us to find a Green's function very, very simple. So if I were to give you this very common second order differential equation, I would like to find its Green's function. Okay, if I'm going to try to find its Green's function, I don't have to do anything else other than use Laplace transform. So I would take the Laplace transform of this equation, both sides. I would get s squared capital Y of s. Now let's assume just for ease we've got rest initial conditions. And so all of these other terms will go away. Plus omega squared capital Y of s is f of s. S squared plus omega squared capital Y of s is big F of s. And so big Y here is going to be 1 over s squared plus omega squared. That's the transfer function. And it's going to be multiplied by that the transform of the driving function. The utility, the beauty of all of this is that if we wanted the solution, we would take the inverse Laplace transform of that product and we would use convolution. But really what we were after here was the Green's function. And by convolution, the Green's function is just going to be the inverse transform of the transfer function, but it's shifted to t minus tau. So the transfer function here is s squared plus omega squared. That's very closely related to this expression. So I'm going to have a 1 over omega s squared plus omega squared. And that's going to give me 1 over omega sine of omega t, where the t has been shifted to t minus tau. And very, very quickly, I am done. I can find the Green's function very simply, very easily, just by using this expression. What's even nicer is that it automatically combines it all. If we were to do this using the old Green's function method, this would be a product of sines and coses, and I'd have to subtract them, and it would be a big mess. And so Laplace transforms have offered us a very sophisticated way of using these Green's functions and coming up with them more easily. It will make our lives very, very easy if we want to solve higher order problems too. There are higher order problems that we can solve and find the Green's function for in just as easy a way as we could for this.